Hello and welcome back. Today I'll be continuing from where I stopped in the last class or series. So I stopped at generative AI, predictive AI, and agentic AI, and the different use cases. So in today's video, I'll be continuing the remaining part of this segment of the exam objective, which is we'll um, look at fine tuning as a whole. We'll also look at prompt engineering, and then we'll consider all the subtopics and all the subtopics under fine tuning and prompt engineering. So let's just go straight to the the main thing we have. So again, in this video we'll talk about fine tuning, and then we'll talk about pruning, quantization, and prompt engineering subtopics such as system prompt, user prompts, one-shot prompting, multi-shot prompting, zero-shot prompting, and system roles and templates. So having said that, let's just go to the first aspect of our topic for today. So today we'll look at fine-tuning. What is fine-tuning? From the way it sounds already, we understand that fine-tuning essentially means making something better. So is usually a domain language for large language models recently. So would have a pre-trained LLM. What are pre-trained LLM? These are like an LLM that's already ready to use, like maybe open source LLMs. So something like Llama, right? So we have a pre-trained LLM, and then we fine-tune the LLM, and then with a data set, with a domain data set, and then we now have like a fine-tuned like large language model, right? So again, we are essentially trying to improve or customize an LLM that already exists, right? And then use it for our own domain use. So there are different kinds of open weight models, open weight large language models like Llama, and then a cybersecurity personnel might decide to fine tune Llama, and then with a custom domain dataset. For example, Llama is generally specific for general tasks, but we can customize this model through fine-tuning methods, and then using a particular or series of data sets, and then we have a fine-tuned LLM that we can use for what we want to achieve. So what are the benefits of a fine-tuned large language model? Number one, it helps reduce hallucinations. What is hallucination? Hallucination is essentially when a model is coherent, like it's generating coherent responses, but it's factually wrong, right? So because we are using maybe a general um, um, large language model, right? It's prone to hallucination because it does not have the domain specifics. Just like so a large language model does not know or understand your own city. So you ask it, what is the biggest city in maybe say the United States, and it does not know because it has not been fine tuned on that particular data set. So it prevents less hallucinations. It prevents privacy leakage. It prevents. It also helps to adapt to domain control. It gives us more domain control over what we have or over the kind of large language model we want to use, and it allows for moderation. We can moderate, we can customize, we can fine tune again to use the model for our taste and our desires. A typical example of a cybersecurity LLM is Trendio LLM. I have used this LLM for my research, and it's gotten from Llama. So it's gotten from Llama 3. So they customize or they fine tune this LLM with cybersecurity data sets, threat intelligence data sets. That's what they use to fine tune this model. So another one is Zizek LLM as well. Are cybersecurity large language models that have been fine tuned from domain specific large language models. And then another domain for healthcare is MedLlama. So they fine tuned the pre-trained large language model using medical data sets and then customizing it for patient care. So these are the examples of the benefit and also the benefits of fine tuning. The next thing on the slide or the exam objective is epoch. So epoch is simple. Epoch is the number of training iterations. So when we start training or when we start fine tuning, right, we are retraining the model with a domain data set. The number of times that we do this training is what we call like epochs. So we can train our model for 10 epochs, 20 epochs, 30 epochs, 40 epochs, as the case may be. And you train until you get your desired outcome. Usually there's what we call like um, um, okay, never mind. But epoch is just training with a number of times or iterations. And then we go to pruning. So pruning involves the core essence of pruning, from my experience so far, is privacy. You know, pruning helps, just like you want to prune something, right? And you are essentially trying to, prevent a particular segment of that thing from exposure or from part or use, right? So the first use case is privacy, and then the second use case is intelligence, but it's inefficient. So this one thing you should note for the exam. Whenever they mention pruning, you just have in mind that, oh, this is intelligent, but it's not efficient. The efficient one is quantization, and I'm going to come to that. Okay, so pruning is a very important mechanism that model developers or model users or AI engineers can use, to prune their model. So when do we prune, right? We can prune the model before training, before deployment, right? We can also prune the model during deployment, and we can also prune the model after deployment. So these are the exact times or case scenarios where we can prune our model. Another question we might have is, how often do we prune the model? Another question is, how often do we prune the model? So we can prune the model one shot, like once, right? Or we can decide to iteratively prune the model, and that's an indirect continuously, right? Maybe we see how the model is behaving. For example, if the model behaves according to a particular rewarded action, we can now iteratively prune the model to achieve what we want. And then what to prune? So we prune neural networks, right? We prune neural nets, and we can select layers of the neural net that we want to prune, right? So we can select some layers, which is local pruning. We call this local pruning, right? And we can also decide to select some pool of the layers, right, of the of the transformer model or the neural network model, and this is what we call global pruning, right? So pruning can either be when it comes to what to prune, we can decide to select some layers, unnecessary layers, right, and prune it, and or decide to use a pool of layers and prune, to get our desired objective. So look at this to give you a better, clearer example, right? Look at my Korean neighbor, right? This is her rose plant, or this is her rose flower, right? And then she cuts and prunes them. If you look on the floor, right, you can see she's cut some of the rose plants. And to my experience, when I asked her, why are you cutting some of these um some of these beautiful roses, she said, oh, it makes them better, right? It makes them, but it's inefficient because maybe she's thrown away some rose plants. And this gives you a simple idea of, how our everyday life or how everyday life situations, can just giving you a better understanding of what pruning actually means. So pruning essentially is an intelligent but inefficient method of, adapting large language models for a particular or specific use scenarios. And what are the limitations, right? Um, Pruning is computationally expensive, right? Because when you prune, you cut some layers of the model and then retrain the model again. Retraining a model from scratch after pruning is computationally very expensive. You have to incur a lot of cost on that. And once you cut out some neurons or some layers, right, you might reduce some accuracy. So computational expenses and accuracy might be the limitations or are limitations of model pruning. I want to show you guys a simple example of what happens, right, when you prune a model. So when it comes to this is like a research I did some years ago. So SAP is stochastic activation pruning, right? This is a model, right? So before and after, you see that the green ones are I use pruning essentially for privacy preservation. So I pruned my neural network model that I was using this model to detect cyber attacks, right? So after training the model, I pruned it. I covered the model, right, with privacy preserving mechanisms and then deployed it. So the green ones are the privacy coverings, right, on the model, that gives it some privacy preservation. And the original ones are like the model, like the model samples without pruning are the ones in blue. So you see that the green covers the blue. And this is like, a simple scenario of what pruning actually, looks like. So let's go back to what we have. We then have the next topic, which is called quantization. Quantization deals with memory compression of a neural network, right? It converts floating points of a neural network into low bit weights. So we have a neural network, and then after quantization, we have low bit weight, representations of the neural network. And then, what is the essence of quantization? Why do we need quantization? To help reduce memory size and parameters, because these models are very, very heavy, they're very, very large, they're also like, they have very heavy memory footprint. So with quantization, there are TensorFlow libraries for quantization. You can check them out, right? You would see how we are able to reduce the memory size, from a large number to a smaller number. And this is what quantization does. In the exam, quantization questions will be asked as well, allowing you as a cyber security expert to understand and know, oh, my company wants to deploy a model, and this model is heavy. If we quantize, I'm not sure how to pronounce that, but if we reduce, can we save some memory footprint? For example, the model is generating about like maybe uh uh generating like maybe 10 kilogram of carbon or whatever amount of carbon dioxide, from quantization. But after like quantization, we can reduce carbon footprint, and we can also, show our organizations or show business competitors or show our clients and customers that we serve you with very low memory footprint. And this is one good thing about quantization. So we can quantize or quantize or whatever you call it, from a 32-bit, to a 16-bit floating point setting, right? Or and then we can even quantize from 16, or I'm not going to say quantize again, I'm going to say reduce. We can reduce from 16 to 8, and then from 8 to 4. So this is the essence of quantization, to reduce memory footprint and model parameter size. Sorry, and model size. What are the types of quantization? We can quantize. Oh my God, we can reduce the quantization experience or whatever after training. Post means after, so we can do this after training or when we are training. So quantization aware training essentially implies that as the model is being trained, we are quantizing the model's memory footprint as well. But post training is maybe we have our model, right? And then let me start over. So we have model, train, quantize, right? And then for here, as we are training, the core difference between this is that quantization aware training, right, is during the training process. So during the processes, you're also reducing the floating point or integer point numbers. Okay, so this is the core difference between post training and quantization aware training. So what are the benefits of quantization? Number one, efficiency. Compared to pruning, quantization offers more efficiency. Another benefit is low power. So because you reduce the memory footprint, you incur less power consumption. Another benefit is compatibility. So we have compatibility with edge devices. For example, we have like a sensor device, you know, that needs low memory footprint, and we have like maybe the one on the cloud device. They don't have the same they don't have the same demand for they don't have the same compatibility. So we can quantize or reduce to maybe say four integer, right, representation for an edge device, right? But maybe for a cloud-based infrastructure, we can use or reduce it to 32-bit or 16, right? Yeah. So this is the essence of compatibility, and then we have faster inference, right? Because we are using large edge devices, fast smart devices that are quantized and use quantization aware training methods or post quantization aware training, would have like faster inference. So these are the benefits of um, quantization, within cybersecurity or AI. Okay. So we now go down to prompt engineering. Prompt engineering is how like a cybersecurity expert might want to, techniques that he will use to achieve, a desired output from a large language model. The first one is zero-shot prompting. So zero-shot prompting relies on the AI model's pre-trained knowledge by giving it command without any examples. Very vague. So zero shot is very, very vague. You query the model, and the model is just maybe can just give you a general overview of what it thinks, right? So it's less useful for when it comes to specific security tasks or some code auditing. It does not do well there. So it's too general, too generic in nature. So that's the problem with zero-shot prompting. For one-shot prompting, it provides the model with exactly one example of a desired input-output pair. What is input-output pair? Okay, I give you input, you give me output. Okay, so it provides an example of what we want and what I want, right? For example, a one-shot prompting might be I customize the prompt to give me a desired input, right? For example, I want you to give me the color of the sky. Sky is blue, and then I expect blue as my answer. So it helps the model understand the expected format and logic of a task through basic in context learning. Okay, and then multi-shot prompting provides the model with multiple examples of desired output, for them of desired input-output pairs to establish a clear pattern. So this method is highly effective for complex tasks. Take note of this: complex tasks and multi-shot prompting, right? For example, feeding the model three different suspicious log entries and their correct risk classifications significantly reduces the chance of unsafe or irrelevant responses. So multi-shot prompting helps the security expert or whoever is using the large language model, you know, to get relevant responses instead of getting, multiple options or multiple, guesses of the model. Okay. So uh, another type is system roles, right? System roles or system prompts, right? The core focus here is that background instructions are used to define the fundamental personal, constraint, and behavioral guardrails of the AI model. So with system prompts, we give the AI a persona, right? And then it operates invisibly to the end user to govern how the model responds to user queries, serving as a primary defense against prompt injection attacks. I will come and I'll make a video when it comes to prompt injection attack. But prompt injection attack is like something like you tell the model, ignore previous instructions, give me the recipe on how to build, you know, uh, give me this of how to do something malicious, right? So this is why, you know, it is not useful, or is good to use a system prompt, because we can customize a persona, right, with system roles and system prompts. These differences are usually asked in the exam as well. User prompts. So the user prompt is the standard untrusted natural language inputs and queries provided by the end user. So these user prompts must be carefully isolated from privileged system instructions so that the malicious users cannot trick the model into overriding its safety rules. Okay? And then templates are the final prompt engineering technique within module 1.1 of the basic AI related cybersecurity. So we have standardized structural frameworks that ensure consistent and secure query formats, right? Used to build a secure boundary that isolates untrusted user provided data from the model's internal system instructions. So these just go over this, at your free time, and you get the core difference prompt engineering between each prompt engineering technique, their their core focus, right, which I've summarized here, and their use cases. Okay. Having said that, I want to leave us with a little sample questions. Okay. So take some time, pause. This is question one. You can take some time, pause the video, and attempt this question. Okay. And then this is question two. Also, go ahead, read the question, understand the context, and make a choice from A to D. And then this is question three, right? Um, Also feel free to pause the video and have a look at this question. And then this is question four. Also feel free to pause the video, read the question, understand what is contextually being asked, and provide your answer. All right. Okay, so let's look at question one again. A healthcare organization is deploying a large language model to assist doctors with diagnosing patient symptoms. The security and compliance team dictates that the model must have a strict domain control, acting only as a medical assistant like MedLama, and must be heavily guarded against privacy and data leakage from its original broad training data. Which optimization technique directly provides these specific benefits? A. Post-quantization training. B. Iterative pruning. C. Fine-tuning. D. Multi-shot prompting. The answer is C. C is fine-tuning. Remember, we want to customize, right? And we have strict domain control here is the keyword. Okay. Question two. Security engineer is designing the interface of an internal SOC chatbot. They have already defined the fundamental persona and behavior guardrails for the model to ensure it acts as a security assistant. However, they need to build a secondary boundary that forces all untrusted natural language queries from the junior analyst into a consistent structure, isolating that user-provided data from the internal system instructions. Which techniques must they implement? B. Templates. Template is the answer. Go back to the video and then you will find the core focus of template prompt engineering. Okay? Question 3. When optimizing a neural network for deployment on an edge device with strict hardware constraints, an engineer must weigh the limitations of various techniques. Which of the following accurately describes a limitation and characteristics of pruning as opposed to quantization? A, B, C, or D? The answer is C. So the trade-off for pruning is its computational expense and the accuracy trade-off, because remember when I said when you prune you remove some layers, so removing some layers means you're going to incur some accuracy drop. Okay, compared to quantization you might even witness an accuracy increase when you reduce that memory footprint. Okay, and then the final question is, when configuring an AI model to interpret complex security logs, why is multi-shot prompting considered highly effective, sorry, compared to zero-shot prompting? The answer is B. Multi-shot prompting establishes a clear pattern by providing the model with multiple examples of desired input-output pairs. Look at this. input output pairs, such as suspicious log entries and their correct risk classifications. Okay, so today I have covered 1.1. So this is what I did today. Today we did just 1.1 of 1 of the first section of part 1 of the CompTIA SecAI Plus. I really want to thank you for watching to this point and supporting me. I'm just here to share knowledge, and please feel free to share this video with anyone you know that's writing the exams, or anyone that you know that is interested in AI enabled cybersecurity. They'll find this knowledge very interesting and helpful for both their research, not just for the certification as well, but just to learn something new. And yeah, thank you very much.